Hello, my name is Willie Kasakula, a student with the University of Rwanda in the African Center of Excellence in Internet of Things. And on behalf of all the three authors of this paper, I present to you the paper titled Temperature and Humidity Control Algorithm for Poultry Farm Control Systems. So poultry farm control systems are embedded systems that are used to control the environment in poultry farms. And by the environment, what I mean is the temperature, the humidity, the air speed, air quality, light intensity, the noise, etc., etc. All the environmental parameters that can affect poultry growth. So controlling the environment in poultry farms has been shown to improve production in poultry farming. You find that the birds tend to be happier and grow bigger when they're in environments that are suitable for their growth. So embedded systems have been used to control this environment in poultry farms. But aside all the other parameters that can be considered, we found that temperature and humidity control consumes a very high percentage of the total electrical energy used in poultry farms. So making temperature and humidity control more energy efficient would end up reducing the cost of production significantly, since it consumes a very high electrical energy. So this paper therefore seeks to find a method to make temperature and humidity control more energy efficient in poultry farms. To do that, the research was broken into these three objectives. First of all, was to analyze all the possible combinations of temperature and humidity states. That's to say, what happens if the temperature is high? What happens when it's low? How about when it's in the recommended range? The same goes for humidity, and the combination and all the possible combinations of these states are what were analyzed. And then based on those analyses, we designed an algorithm that is going to utilize that information to make the control more efficient. And then this algorithm was to be simulated and compared with the traditional algorithm to see if it is really necessary to use it to measure the amount of savings that were being shown by this algorithm. So the environmental scenarios were as follows. From A to C, we analyzed low temperature with high humidity, low humidity, and recommended humidity. From D to F, we analyzed high temperature with high humidity, low humidity, and recommended humidity. And from G to I, we analyzed recommended temperature with high humidity, low humidity, and recommended humidity. And we see that the very last one, I, we have recommended temperature and recommended humidity, which is the desired state of the environment. So, but we find that the recommended temperature and recommended humidity are different for different breeds of poultry. So this algorithm was designed to be generic for all the breeds of poultry. That's why the recommended temperature and recommended humidity are passed as input to the algorithm. So here's the algorithm. As input, it takes the current dry bulb temperature, the current relative humidity, the recommended temperature range, and the recommended relative humidity range. And after it does its calculations, the output of the algorithm is an instruction of the action to be taken on the environment. And these actions may be to heat, to cool, to humidify, to dehumidify, or to do nothing. So here's how the algorithm goes. First of all, it checks if the temperature is below the recommended temperature range. If it is, it calculates the resultant relative humidity if temperature is to be raised to the recommended range. Now, if this resultant humidity after raising the temperature is above the recommended humidity range, it means we have excess moisture in the air that needs to be removed, because if we don't remove it and we proceed with heating, we will be heating unnecessary moisture in the air. So we proceed to dehumidify until the humidity is in a range where it will be in the recommended range after raising the temperature. When we do that, that's when we heat the air to the recommended temperature. But if the temperature is above the recommended range, what we do is just the same. We calculate the resultant relative humidity if the temperature is to be dropped to the recommended range. And then if this resultant humidity is above the recommended humidity range, we dehumidify first to remove the excess moisture in the air, and then we cool the air to the recommended temperature. But if the temperature is not above the recommended range and it is in the recommended range, what we do, we check the humidity now, since the temperature is in the recommended range. If the humidity is above the recommended range, we dehumidify. If it is below the recommended range, we humidify. But if it is also in the recommended range, then we do nothing, since that is the desired state. So after the algorithm was designed like that, we checked its time complexity. And we see that if the temperature is below the recommended range, the algorithm does 2 comparisons and 2 arithmetic operations. If the temperature is above the recommended range, the algorithm does 3 comparisons and 1 arithmetic operation. If the temperature is in the recommended range and the humidity is above the recommended range, the algorithm does 4 comparisons. If the temperature is in the recommended range and the humidity is below the recommended range, the algorithm does 5 comparisons. Therefore, in the worst case scenario, the algorithm does 5 operations, and in the best case scenario, the algorithm does 3 operations. So the time complexity of the algorithm is linear, which is big O of n. But since the input to the algorithm will always be constant, therefore n is equal to 1, we find that the time complexity of the algorithm is constant. It's big O of 1. So after the time complexity was analyzed, then the algorithm was simulated. But before we simulated the algorithm, there were considerations to be made. First of all, when heating or cooling, we were adding 1.5 kilowatts of heat, or removing 1.5 kilowatts of heat per 10 square meters. And when we are humidifying or dehumidifying, we were either adding or removing 0.001 kgs of water per kg of air. And this simulation was doing per second calculations. But the data which was used for this simulation, which was collected from a room, was collected every 15 seconds, even though the simulation was doing per second calculations. So to do that, the simulation was taking the temperature and humidity value from a row in the data, and then it passes it to the algorithm, which returns an action to either heat, cool, humidify, or dehumidify, or do nothing. And then this action is simulated. And the resultant humidity and temperature is passed to the algorithm in the next iteration. And this goes on until we reach the next row of data. And then when we reach the next row of data, we consider the effect on the temperature and humidity without the simulation, and the effect on the temperature and humidity with the simulation. These two are added, and then we proceed to the next row of data and simulate the next second and the next one, going on until we reach the end of the data. So we found that the results were as this. The time that the heater spent running in the simulation was almost the same for the traditional and proposed algorithm. But the number of times the heater was switching on and off was very high when using the traditional algorithm than when using the proposed algorithm. We see that the traditional algorithm, it ran for it was switching on and off 55 times, while it only did 4 times when using the proposed algorithm. The time the cooler spent running was also almost the same for the traditional and proposed algorithm, but the number of times it was switching on and off was double when using the traditional algorithm than when using the proposed algorithm. But the real difference, the most significant one, was shown in humidification, because when using the proposed algorithm, the humidifier only ran for 3 seconds, but it ran for 52 seconds when using the traditional algorithm, which is 17 times more. And the number of times it was switching on and off was very high when using the traditional algorithm, 37 times, as compared to 2 times when using the proposed algorithm. Same thing for the dehumidifier, which ran for 56 seconds when using the proposed algorithm, but ran for 94 seconds when using the traditional algorithm. And the number of times it was switching on and off was almost double when using the traditional algorithm than when using the proposed algorithm. So what do these results mean? To determine that, first of all, we consider the standard humidifier, which has a power rating of 60 watts, and the standard dehumidifier, which has a power rating of 298 watts. So we see that when using the traditional algorithm, the energy used in the humidity control was 28,012 joules, while when using the proposed algorithm, the energy used was 16,868 joules. This means that when using the proposed algorithm, we have a 40% savings in the electricity costs for controlling humidity. Also, the actuators operate in rapid on and off cycles when using the traditional algorithm as compared to when using the proposed algorithm. So the rapid on and off cycles increase the risk of mechanical failure, which means when using the proposed algorithm, we are reducing the risk of mechanical failure in the actuators. In conclusion, we see that the proposed algorithm provides up to 40% in electrical energy savings for controlling humidity. The time complexity of the algorithm is effectively big O of 1, which makes it very suitable for operation in low power edge devices. You do not need very complex architectures in your solutions for poultry farm control systems to run this algorithm. And the proposed algorithm reduces the mechanical failures in the actuators by reducing their rapid on and off cycles. So effectively, this proposed algorithm shows potential to reduce the operation costs of poultry farming greatly, since it introduces savings, it reduces the risk for mechanical failures, and it can run in very low power devices. In future research, the algorithm may be improved by passing it with parameters like actuator power ratings. So in such a case, the algorithm would bias the savings to the high power actuators than the low power actuators, since reducing the runtime of the high power actuators may result in higher electrical energy savings than when reducing the runtime of the low power actuators. Ladies and gentlemen, thank you for your time. That was all we brought for you today.